In this video, we'll derive the sampling distribution for a sample proportion p hat. We'll use this sampling distribution whenever we're conducting inference for a population proportion p. The data in situations like this will be categorical. The assumptions we need in order to do this derivation are these. The data must come from a properly randomized design. The sample observations must be independent. And third, the sampling distribution must be normally distributed. And we can verify that these assumptions are warranted by checking these conditions. If the data come from a random sample or from random assignment to treatments in an experiment, then we have a properly randomized design, and assumption 1 is warranted. If the second condition is met, the population is at least 10 times as large as the sample, then we can assume that the sample observations are at least approximately independent, and therefore the second assumption is warranted. Thirdly, if we can expect at least 10 successes and 10 failures in the sample, that is, n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10, then we can infer that the sampling distribution will be at least approximately normally distributed. Now here's the actual derivation itself. We're going to assume that those conditions are met. They're all conditions that are under control of whoever is doing the research. We can determine the design of our data gathering. We can determine if the population is at least 10 times as large as the sample, and we can determine that we have a sufficient sample size to guarantee the third condition is met. So all of those things are under our control as researchers. Now, if we want to conduct this kind of inference, we'll start with this basic situation. We have a large population in which a proportion p has a certain characteristic. Now, this is a population proportion that has that characteristic. Now, we're going to draw a simple random sample or some other random sample of size n, and in that sample, we can let x be the number of individuals in the sample who have the characteristic of interest. In the language of binomial distributions, x is the number of successes in the sample. Now, if the population is greater than 10 times the sample size, then the sample observations are approximately independent, and x is approximately binomial. It'll have a binomial distribution with parameters n and p. The sample proportion that has the characteristic is p hat, and p hat is simply x divided by n. It's the number of successes in the sample divided by the sample size. We want to know how this p hat is distributed in terms of its center, its spread, and its shape. Well, the center is quite simple. The center is the mean of the sampling distribution of p hat, and the mean of p hat is just the mean of x over n. But that's just a linear transformation of x. So the mean of x over n is just the mean of x divided by n. Since x is binomial, the mean of x is n times p. N times p divided by n is just p. Well, that's nice. The sampling distribution of p hat has its mean at p. In situations like that, where the mean of the sampling distribution is equal to the population parameter, we say that the statistic is an unbiased estimator of that parameter. And in this case, p hat is an unbiased estimator of p, the population proportion. Secondly, the spread. The standard deviation of p hat is the standard deviation of x over n, which is just the standard deviation of x divided by n. Now, from our binomial distribution, we know that the standard deviation of x is the square root of n times p times 1 minus p. We're going to divide that standard deviation by n. And the way we're going to do that, we're going to bring that n inside the radical and square it when we do that. And then we're going to cancel that n up there with one of these n's down here, and we're going to wind up with the square root of p times 1 minus p over n. So this is the expression for the standard deviation of the distribution of p hat. Now, the standard deviation of p hat, sigma p hat, is a measure of the sampling variability of p hat. It depends on the sample size n, not the population size. There's nothing in here about the population size. But you see that since n is in the denominator up here, sigma of p hat varies inversely with the square root of the sample size. And that means we could reduce sigma of p hat to any desired tolerance by just increasing the sample size sufficiently. Thirdly, the shape. If condition 3 is met, the success-failure condition, then x is approximately normally distributed. And therefore, since p hat is equal to x over n, p hat is also approximately normally distributed. And what we wind up with is this. Here's a little picture of the sampling distribution of p hat. Now we have to make sure that the conditions are met. We have a random sample or a random assignment to treatments in an experiment. We have a population that's at least 10 times the sample size, and the number of successes and failures is expected to be at least 10. If those conditions are met, then this is the sampling distribution for p hat. It has its center at p, that is the mean of p hat is the population proportion p. The standard deviation or spread is the square root of p times 1 minus p over n, and the shape is a normal distribution, the familiar bell curve. So it's quite simple. It all depends on the conditions being met that we use to derive this. If those conditions are met, we can use this proportion. We can use the sampling distribution for the sample proportion p hat confidently when we conduct inference for p.